Hello students, today we will learn about the certain properties of the capacitors and their arrangement in series and parallel. So let's start. After knowing about the capacitors, now we want to make a combination of the capacitors. We can combine them in series or we can combine them in parallel. So let us see what happens when we connect the capacitors in a series combination or in a parallel combination. And that is very easy and very interesting, and that gives us a very scoring for all the numericals and the derivations we can do. All this thing is very scoring, but the concept is very simple. So let us go to that easy concept, and once it is clear, then you will make a fun doing all the numericals and getting your answer correctly. So let us say we take two parallel plate capacitors. So we are having two parallel plates which are at some distance, and between them is any dielectric medium or any insulating medium. It may be air, it may be vacuum, it may be any dielectric. And so one charge with plus Q and another charge will be minus Q on each of these plates. And so it is having the charge plus over the surface over here, and here the charge will be minus over the surface because these are two conducting plates, and this is the property of a conductor that all the charge resides on the surface. If you want to go into the detail of how conductor behaves in the electric field, you can also refer to the lecture given below. But as for now, just remember that the charge resides only on the surface. So here we have shown the charge is residing on the surface for plus Q and minus Q. These are two plates. So simply we are combining two capacitors in series. So say this is a capacitor. Now I connect one more capacitor in series. So there is another capacitor which is connected in series to this combination of two capacitors. So this is again plus Q and minus Q. So here also we can show with the symbols plus and minus on the plates of these conducting parallel plates. So let us see. Say this is capacitor 1 whose capacitance is C1. This capacitor 2 whose capacitance is C2. So now these two are in series combination. If the one end of the one is attached to the one end of another, then we call it a series combination. So in series combination, if we see the net charge, then here it is plus and minus, and these charges are equal. So this is plus Q and minus Q. That will give the net charge as 0 for this capacitor first, and similarly for the second capacitor, our net charge Q comes out to be 0. So we cannot write anything in terms of the charge. We have to remember the magic formula. C is equal to Q upon V. This is the magic formula for the capacitance. So we want to calculate the capacitance for these two capacitors which are combined in series. So Q net Q is 0 for individual capacitor. So let us move to the potential. So whenever there is a charge transfer, there is a potential drop against these two plates. So let us say that the potential drop in the first capacitor is V1 and the potential drop in the second capacitor is say V2. So we want to write down in terms of the potential drop. So the total potential drop will be the sum of potential drop across capacitor 1 plus potential drop across capacitor 2. So from this formula, use the magic formula. C is equal to Q upon V. That gives the value of V as Q upon C, right? So put the value for first capacitor, charge is Q on each, capacitor is C1. The second capacitor, that is charge is Q on each plus the capacitance is C2. And the total, if you write down, V is the total potential drop. So Q is common in both these terms. So we can take Q this side. So V upon Q is equal to 1 upon C1 plus 1 upon C2. And from the magic formula, V upon Q, what is V upon Q? V upon Q will give you us, V upon Q will give us the value of 1 upon C. So from here we can write down 1 upon C is equal to 1 upon C1 plus 1 upon C2. Right? So if you are having a combination of two capacitors in series, then we got this formula for the combination, that the total capacitance 1 upon C, if C is the total capacitance, then 1 upon C is equal to 1 upon C1 plus 1 upon C2. And similarly, we can connect any number of capacitors in series combination. So similarly, if we generalize up to the maximum, say any n number. So if we connect n such capacitors in series, and such capacitors that I have drawn to above, so we are taking n similar capacitors in series, then we will be generalizing this term. 1 upon C is equal to 1 upon C1 plus 1 upon C2 plus 1 upon C3 plus 1 upon C4, plus we may continue this up to the capacitance of nth capacitor 1 upon Cn. So this is a general term we get for the capacitors which are connected in series combination. So we get this expression for n number of capacitors which are connected in series combination. That is a general formula. So whenever you see, then you can calculate this. And the thing is that when we go for the resistor, then we are getting this exactly opposite. We will do for the parallel combination also. So whatever we get for the parallel for resistors, we get it for series of capacitors. And let us move on to the parallel combination. Now let us quickly move to parallel combination when these two are connected in parallel to each other. So let us say that we are having two capacitors which are connected in parallel. So this is our capacitor number 1, which is having the capacitance of C1, and the charge is say Q and minus Q here. So this will be plus, 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 and this will be minus, 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 right? And if we connect both the ends to another capacitor, this is another capacitor we are using, and if we connect both the ends to this, then this is known as a parallel combination. This plus, 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 and minus, 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 minus. And this is having a capacitance of C2. Again, we can add on plus Q and minus Q here. So whenever these two are in parallel, that means the potential difference that is applied across both of the capacitors is same. So whenever we are having a parallel combination, that means the potential difference, the value of V will be same across these two capacitors. Okay, so just remember the magic formula, C is equal to Q upon V. Since V is same, so we can take the charge as different. Say for the first capacitor, we can take it plus Q1 minus Q1, and for the second capacitor, we can take it plus Q2 and minus Q2. Why we are taking this? Because the charges may not be the same, right? The voltage difference that we are applying is the same, but the plate charges plus minus Q1 capacitor 1 and plate charges plus minus Q2 on capacitor C2 may not be the same. It is not necessary that these two are same. Then for this we can write down as, because we want to write down Q now. If Q is not the same, then we are terming these as Q1 and Q2, plus minus Q1 for C1 and plus minus Q2 for C2. So from this magic formula, Q1 comes out to be C1 into V, because in parallel combination V is same. So Q1 is equal to C1 and similarly Q2 is equal to C2 V. Now if you want to calculate the total capacitance, then since the voltage is same, then you can add up the charges. So the total charge will be the sum of charge on capacitor 1 plus charge on capacitor 2. So put the value, Q is equal to, this is C1V and this is C2V. The only thing is that V is same because these two are in parallel combination. So now we can write down this as V is common in both the terms. So we can take V this side. Q upon V is equal to C1 plus C2, and again the magic formula Q upon V will give us the value of C. So the total capacitance is the sum of capacitance of first capacitor plus capacitance of second capacitor. So this gives us the formula of the total capacitance of two capacitors which are connected in parallel. So this is exactly opposite to what formula we get for resistors. For resistors, it is like inverse in relation, and 1 upon R is equal to 1 upon R1 plus 1 upon R2. But for capacitance, we got this formula as C is equal to C1 plus C2. And similarly, if we connect and such capacitors in parallel. So similarly, if and capacitors and such capacitors are attached, are in parallel combination, or we are arranging these in parallel combination, then we can generalize the simple formula. So we can write down the total charge Q is the sum of charge on first capacitor, charge on second, plus charge on third, and we can take it up to the maximum value charge on nth capacitor. So this comes out to be, from the magic formula, Q is equal to CV. This is C1V plus C2V plus C3V and so on, and this is C and V. So here V is common throughout, so if we cancel out the V throughout, then C is equal to C1 plus C2 plus C3 and up to Cn. So whenever you see the capacitors in parallel, their both ends are connected, then simply the voltage is same and the capacitance will simply add up. And whenever these in series, then you have to use the previous relation, 1 upon C is equal to 1 upon C1 plus 1 upon C2. So these are the two simple derivations we can see, and whenever there is a combination of series as well as parallel, then you can use both the formula and you can solve all those corresponding numericals. Now we want to calculate the electrostatic energy of a capacitor. So let us take a parallel plate capacitor. These are the two parallel plates I am drawing. This is our plate 1. Say this is a plate 1 and this is our plate 2. So these are the two parallel plates which are conducting plates, and these are capped at some distance. Say this distance is small d. So the distance between these two plates is d. And these are capped at some distance small d. So the distance between these two plates is d, and say this is having a surface charge density of plus sigma and this is having minus sigma. So here we will be having positive charges. So this is a conductor, so all the charge will reside on the surface of the conductor. If you want to know about this property of the conductor, you can refer to our lecture where we have discussed that what happens when the conductors are placed in external field, external electric field. Then you will come to know how this behaves. But as for now, we can only say that this plus charge or minus charge, it resides on the surface of this conducting plate. So this is a conductor, and then say the capacitance C we want to calculate for this parallel plate capacitor. We have already derived a formula, then C is equal to epsilon naught A upon D, and E we got initially was sigma upon epsilon naught. Right? So here we are doing this, and this electric field E is between the two plates of the capacitor in the middle region, and this is E is equal to sigma upon epsilon naught. The volt electrostatic potential we got was E into D. D is the distance between the plates and A is the area of each plate. And this distance D we are taking is very, very less than in comparison to the area A of these plates. Right? So this is acting here. There is a dielectric medium. So what we can say that this will act as a capacitor, and there is a transference of charge from here to here through the dielectric medium or through the vacuum, whatever is insulating medium present here. So we call it as a capacitor. It is its capacity to store the charge. Using the magic formula, we can write down C is equal to Q upon V. So the ability of a capacitor to store the charge maximum for the minimum value of V is its capacitance. And it depends on its physical properties, because for a given Q, it has some value of V. So now we want to calculate the energy of a capacitor. So we want to shift this plate from here to somewhere here. So this plate is now shifted here at this point, and the distance I have traveled from the initial value, so this distance is x. So I have shifted this plate to the distance x because it is the same plate I have shifted, so it will also have the surface charge plus, and it will have the same surface charge density because that is due to the continuous charge distribution over here. So in the new position also it will have the surface charge density as plus sigma. Now if you want to calculate the work done, the work we are doing, the external work we are doing on shifting this plate to the distance x, then this will be equal to the force we are applying on this plate to shift and with the distance we have shifted. Okay, initially the distance is d, but we are shifting it with the distance of small x only. So the work done external, the work we are doing, is equal to the force we have to apply and multiply with the distance, because work done is equal to force into displacement. So x is the displacement we have done and force is the external force. Now if it comes to the external force, and here it is having the electric field as E. So the force should be Q into E. So the charge, if you write out in terms of sigma is equal to Q upon A. So whenever you want to write out the charge, Q will simply be sigma into A, sigma multiplied with A. So this F should be Q into E, but what happens here, that as I told you, this is the conducting plate. So all the charge which is residing near the surface. So here this is the surface, and all the charge of the conductor, whatever is the extra charge given to the conductor, resides on its surface, never on the interior of the conductor, because for the interior of the conductor E is always 0. That is one of the thumb rule when I told you. And just refer to my lecture where we keep the conductors in an external electric field. The link is given below. Just go quickly to that lecture and find out how the conductor behaves when they are kept in external electric field. So here we are applying some voltage. So there is an external electric field. Since this is a conducting plate, so inside the plate electric field is 0 and all the charge is residing on the surface of the conductor. So if we calculate E is equal to sigma upon epsilon naught, then this is equal to sigma upon, this is the average of all these. So this will be equal to, the force will be equal to Q and sigma upon 2 epsilon naught. So this is the force that is working, external force we have to apply across it. Now put the value of work done, external work we are doing, is equal to put the value of external work, that is Q sigma upon 2 epsilon naught, and the distance is x, we have shifted this plate. So the work done, that is external work done, is equal to, again put the value of Q. So Q is equal to sigma into A. So this is sigma square A. One sigma is already there, and one sigma we got from Q is equal to sigma into A. So this sigma square A upon 2 epsilon naught multiplied with the distance x. So we get this, the work done externally is equal to half of sigma square A upon epsilon naught into x. Just remember here that the force that is applied is not equal to QE, since we have taken an average, so it is always QE upon 2. And the next thing I am doing is that I am just simply multiplying it and dividing it with the epsilon naught. So we get this value as, so we simply get this value as, the work done external is equal to half of, now this is sigma square upon epsilon naught square, then this is epsilon naught A into x. So this is sigma upon epsilon naught. So the work done external will be equal to half epsilon naught and this is E. Sigma upon epsilon naught, we can substitute it E, so half epsilon naught E squared, and then it is A into the distance we have to use. So all this work we have done externally, it will go into the potential energy. It will work as the potential energy of the system. So if you want to write down, so all the work we have done, it will go as the potential energy of the system. So if you want to calculate the energy, then it is equal to U. Potential energy is represented with the symbol U. So we can write down U as U is equal to half epsilon naught E squared and multiplied with A dot x. X is the distance we have traveled, and since it's A into x, that is the area into the length, so we can also write it this down term of the volume. So this is the energy. If you want to calculate the energy density, then you can write down the energy density as is equal to energy stored per unit volume is divided with the volume. So if you divide it with the volume, that is A into x, then we get the energy density or the energy stored per unit volume is we get the expression for energy density is equal to half epsilon naught E squared. So whenever you are calculating the energy density, then simply use the expression half epsilon naught E squared. That gives us the potential energy density of this system for a parallel plate capacitor. So what is the formula? Half epsilon naught E squared. That is a very simple derivation you can do, and always remember this formula. So that's all for now. If you like this lecture, then like and share, and please subscribe to our channel Physics Class so that you can continuously receive notification for all the new lectures. Thank you.